Hello, everybody, and welcome. Let's go ahead. This is the next exercise about path integrals. All the time we're talking about path integrals now inside exercise sheet 10.1. But this is the first time we really are forced to explicitly calculate such a path integral. If you remember, even in the previous sheet, we have often been concerned with the situation that either a certain vector field is given or a corresponding potential function, or even both. And then we keep checking, is this vector field the gradient of the given potential, or in the other case, do we find a valid potential? Why do we do this all the time? Well, the reason is every time you find that your vector field is conservative, which means it is the gradient of an existing potential, it's much easier to evaluate a certain path integral of this field along a certain path. No matter whether this path is closed or whether it's open. In both cases, as we saw last time here, it's possible to, you could say, to indirectly solve the path integral without even setting it up explicitly. Instead, to say and to find out that any closed path integral always results to be 0, while an open such an integral along an open path results to be the difference of the corresponding potential function between starting point and end point of this path. So this time it's different. Why? Well, first of all, as a remark, this is a three-dimensional example, which is better because in practical situations you will most often be confronted with, of course, with the full three-dimensional space in your setting. Well, but this is not the reason why it's different. The reason why it's different is you will find by yourselves by just looking at this vector field. It strikes you that the three different coordinates x, y, z appear in places where we wouldn't necessarily expect them. In other words, this is sort of a perturbation. You know what I mean? So I find the z coordinate in the x component. I find x in the y component. I find y in the z component. This is quite chaotic, you could say. So it's sort of a perturbation. And this is typical for so-called vortex fields. We have been concerned with vortex fields already. You remember when we're talking about rotation, even divergence, and these first order differential operators, which are very important in that context. But on the other hand, we have arrived on the backhand side of the same coin. You know, the front side is, you could say, is differential operations like rotation, divergence, gradient, and the backhand side then is everything about integrals. Okay, so now anyway, with a little experience, you will know that this vector field definitely has some rotation. It is not necessarily a purely it's not necessarily a perfect vortex field. It may also have certain divergence properties of radiality, but it's not free of vorticity. That's what I see, because if you don't see it, just take the rotation operator on this field. That's one very good method to prove that a given vector field is not a gradient field. You must remember, you might remember way back here that we once found this important theorem, sorry for jumping here, which states, no, it's not the right position. Where is it? I guess it's here. Just a second. Yeah, here it is. Which states that once you have the gradient of a potential, which means you have a gradient vector field, or in other words, a conservative field, you will find that the rotation of this field must be 0. Why? Because due to conservation, any closed path integral must be 0. So the other way around, it's also possible to use this. It means to show that this field is this time is not conservative, let me jump back to our exercise here. No, sorry, where is it? Two possibilities. Either show that the rotation of this vector field is non-zero, or try and find a valid potential and then but come to the conclusion that it does not exist. So we won't do neither nor, okay, you know, because we don't have the time now. But we just suppose this is a non-conservative field, which is already stated in the title here. So because it isn't conservative, we have no other chance than setting up and solving the path integral explicitly. Let's start to do so, and please learn how. Because this is probably the only time we go through this procedure in detail. So please remember every step and also the order of steps that need to be taken. First step, write down, I call it W because it might be the mechanical work. As a result, write down your path integral in symbolical form, saying we want to integrate along the path P. Our vector field is called capital F vector of x vector, and then we integrate along the path by using differentials dx vector. Now, replace everything that contains x in the sense of our positional coordinates, replace everything by p. Why is it? Well, this is the path. The path is sort of a spatial curve running along. It has a certain curvature along all the three spatial dimensions, but as always, it is given as a so-called radius vector function with the three spatial components: x component, y component, z, or you can also say first, second, and third component, always expressed using a certain auxiliary variable. In most of the cases, it's called t. And very often, it's, at least in the application, it's interpreted to be the time in seconds, classical time, okay? So, and this is just given, it's sine of t, negatives cosine of t, and exponential e power t. It's, as you see, it's a little non-technical, it's just a mathematical example. And then always it's important to know in which range, well, let's say domain or interval this independent variable t will vary. In this case, it starts at value t equals 0, and then it's increased up to pi over 2. So that's all we need. And now, well, just referring to what you learned in the lecture, there is a certain substitution. Everything which is expressed with spatial variables, even in a vectorial form here, must be expressed sort of in a temporal manner, if I may use the physical phrases, okay, for you to understand better, possibly. So in this notation, we know the field strength and direction at every point in space using just simply any radius vector with coordinates x, y, z. So we know where we have, at which position in space we have which field vector. Now we take this radius vector to be evaluated at one point on this curve, on this path, because this is what we want to do. We don't want to know well, the properties of this vector field everywhere in space. We're just interested in this field along the curve, along the path. And so it makes sense to put in these radius vectors describing the path into the vector field. So that's what we mean if we write, I'm sorry, there's a vector symbol missing here. We have to express our field vector just using t. So, and I will show you how to do it. Then next, because this is a valid substitution, just imagine this is you could say this is a certain infinitesimal movement in space. This is replaced by an infinitesimal interval of time increasing. So what is the relation or the connection between a little movement along in space, and the corresponding time interval, well, it's the velocity. And this is the mathematical version of velocity. This is x vector dot of t. It's simply the first derivative of our radius vector along the path. So this is a very nice concept of calculating which spatial direction and how fast, you could say, we move along the path if we increase our auxiliary variable t by a certain amount. That's a good idea. And in the end, there's, of course, there's a clean derivation of this whole transformation here. So this has to be done. And then we have to perform, very importantly, this scalar product also, so that we get a simple scalar expression just containing one variable. And then in the end, we have a certain term of t just to be integrated over t. So after all, this is a single integral. It's not an iterated integral. That's a sort of advantage. We express everything which is high dimensional by a certain substitution to be a simple integral, yes, over just a simple variable t. Now, the first step, how to put in these vectors in sort of setting them in, putting them into this field. Well, it's relatively easy. You just say, these are the components of our point in space, which is on the path. So this corresponds to the x component. This is the y component. This is the z component of a certain position in space. So now looking at the field, everywhere I find x to appear, everywhere x is replaced by the first component of the radius vector describing the path. Everywhere y appears, it is replaced by the second component, and everywhere z appears, it is replaced by the third component. That's all. So look what I'm doing. I find negative z. Looking here, I take the z component of the radius vector and fill it in instead of z. So I get negative e power t. That's it. Here I find x. This is the first spatial coordinate. So I take the first vector, radius vector component, sine of t instead of x here. And last but not least, negative y is replaced by negative this component. So negative cosine of t gets positive cosine of t. That's all. This is actually, if we use the physical wording, what you see here, it is the field vector at some time. So if t is the time, and this tells me which is the temporal movement along the path. So let's just take t equals, say, 1, okay? Maybe this is measured in seconds, or the time interval is from starting time to 1.5 something seconds. And after 1 second, I want to know where I am. So I just fill in t equals 1. I have the sine of 1, negative cosine of 1, and e power 1, which is just E, Euler's number. So this would be a point in space. And at this time, at this point in space, this will be my field vector. So here I can just set in the t value, and I will find which is my valid field vector. You could say this time I have lost the information where this field vector is valid, but now I know when it is valid on this path. I think sometimes it helps to give this vivid explanation of what we're doing here, but otherwise forget it. It's just a technical procedure, right? So what do we need? We need the x dot vector of t, which is just found by differentiating these components regularly for t. So what is the derivative of sine of t? Of course, it's cosine of t. Derivative of cosine of t equals negative sine of t. The negative gets positive, and then this stays as it is. As you know, exponential term gets remains unchanged by differentiating. So that is our x vector dot of t, you could say our velocity vector along the path. Now perform the scalar product in the usual way, just taking the products and summing them up. So I get negative e power t times cosine of t plus next contribution sine of t times sine of t, which is sine squared of t, and then plus cosine of t times e power t. Now we're lucky because these two terms cancel out. You see here's a minus sign beforehand, and otherwise, well, the factors are exchanged, but it's essentially the same. Here positive, here negative, they cancel out. It remains to be just the sine squared of t. Now, remember, this is not the first time we encounter an integral of this sort, so I refer to any handbook again, looking it up in an integral table, whatever. It's a standard integral. And I forgot to tell that, of course, we also have to set the limits of this integration from 0 to pi half. These are values for t, of course. So after writing down the primitive function, which is 1/2, and then in parentheses or brackets, t minus sine of t times cosine of t. You may remember we've used this before. And then filling in, the values for starting value of t and final value of t, 0, pi half. You remember that we have to set in pi, the upper limit first. So we get 1/2 times, now look, pi over 2 for t. That's why I put pi over 2 here. Then minus sine of pi half times cosine of pi half, where the cosine of pi half is 0, so I get 1 times 0. There's no contribution. And also by subtracting the value at t equals 0, I find that 1/2 times 0 minus sine of 0 times cosine of 0 is everything 0, right? 0 minus 0 times 1. So that's all. In the end, it remains to be 1/2 times pi over 2, which is pi over 4. So this is a mathematical example, but please understand that the result of such a calculation must be a simple number. It's not a vector. It tells us how much work such a force field would have to perform on our test particle or test body when the test particle or body is moving along this path inside this field. So this is our point of view, okay? Saying that this field operates on this test body or test particle, thereby, carrying out a certain amount of mechanical work. So that's the result.